Hi, welcome to What's Next, a seminar series presented by IBM Research, in which we spend time with some of our scientists and researchers learning about the exciting work they do. I'm Shaheen Parks. I'm a content strategist here at IBM. And I'm so pleased today to be joined with not one, but two guests. Next to me, I have Dr. Thomas Asche from Evonik Industries.
Thanks for having me.
So glad you could join us. And we have Dr. Jie Chen, who is part of the MIT IBM Watson AI Lab based here in Cambridge. Today, Dr. Chen will be talking with us about using graphs and grammars to automate drug and material discovery. And one of the key benefits of the methods that he'll talk about today is that it requires a very small amount of data to be effective. When we compare it with other methods that you might use to achieve similar results, those methods would need orders of magnitude more training examples to get to even similar levels of effectiveness. Dr. Chen has degrees in computer science and mathematics, and his research interests include statistics, machine learning, and scientific computing. Dr. Asche has a background in chemistry and material simulation, and at Evonik, he is responsible for data science in the research and development organization, and he's part of the effort to move towards a digitization of R&D. Today, Dr. Asche will be able to provide a very complementary industry perspective on the research work that Dr. Chen will talk about. With that, I'll hand it over to Jie.
Thank you, Shaheen. Hello. I'm here very excited to talk about a joint work with MIT recently that generate molecules by using a very small amount of data. So this is an exciting innovation by using graph and grammar. I'm going to talk about the details of that. Drug design and material discovery amounts to generating a good candidate set of molecules so that we can screen them and find the ones that we need. So generating molecules is an important step here. In the past decades, deep learning methods and AI methods have been flourishing in this regard. These methods, called generative models, they are able to learn from a set of molecules and generate new ones. A general limitation of these methods is that they require a large amount of training data. So the method that I'm talking about today would be using a very small amount of data, and it is very data efficient. For example, it is able to use only a dozen training examples that can already generate molecules whose quality are as good as the deep learning methods, which actually requires nearly 100,000 training examples. So in these methods, we will be treating a molecule as a graph and then learn graph grammar to do the job. If you think about getting molecules that are of good use to us, this is like finding a needle in a haystack, because all the possible amount of molecules are actually very vast. So this such space, according to certain estimation, would contain 10 to the 60 molecules for drugs. And if we talk about other applications like materials and polymers, then the such space will be even larger. So the approach we are taking here is like a circle. So we'll start with treating data like molecule here as a graph. Then we'll be learning a graph that can generate these molecules. So the graph grammar here serves two purposes. One purpose is that it is a generative model, can generate new molecules. But the other use of it is that it can also give us a very useful tool to get representations of a graph so that we can use them to get better computer predictions of the molecule properties. Now, predicting these properties are actually also an important step here, because otherwise they have to be done by a human being who goes to the lab and do tests or do simulations. The computer predictions would actually speed up this process. And furthermore, with the computer predictions of the properties, we can now apply numerical simulations, and numerical optimization to find the regions of molecules that are good candidates. So this would reduce the amount of candidates that we need to screen out when we find the ones that we need. So our work here focuses on the first step here, which is to learn a graph grammar by using a small set of molecules.
Yeah, actually, That is pretty interesting, G, because I mean, you mentioned the entire space of small molecules. It's like 10 to the 60s, something like that. But actually, if you look into the chemical industry, we are very limited in what we actually would like to do on large scale assets that we have. So we need to already focus at the beginning to generate those molecules that are of interest to us. And we definitely see that these methods can be helpful there.
Exactly, right. So the grammar we are doing here is actually a good innovation in deep learning because this is a tool for us to narrow down the search space and to identify the good things that we need, right? So I think grammar is actually of most use to us. When we learn a new language, we learn a grammar, and when we learn to write a program, we also learn grammar that specify how a program should be. So effectively, a grammar is a set of rules that tells us how to compose a complicated object, either a sentence or a computer program. It turns out that graphs, which are actually the things that we use to model molecules, also have grammars. And that is the gist of our work here.
So when you say that the grammar is essentially a set of rules, is that similar to how we might describe an algorithm?
Yeah, exactly, right. So like a program, right? So a program contains a lot of statements, and these statements are in certain order, which actually forms the algorithm that tells us if we do the first step and then the next step, then eventually we complete the job, right? So the grammar here is actually also provides us all these elements, and we just need to figure out what are the steps in order to compose a graph that we need.
Yeah. And actually, if you look into the education of chemists, it's basically the same. So you learn a new language, but that language is not meant for communicating with people, but it's meant for communicating with scientists. So you learn chemistry basically as another language, which is foreign in the beginning. But once you get, let's say, a better feeling of it, then you are somehow fluent in chemistry and you can actually speak that language. Basically the same as you speak English, right?
So the chemist is learning the grammar.
Exactly, yeah.
I love that metaphor, right? So chemistry is also a language, so let's learn it. All right, so how do we learn that? First of all, we look at a graph. We look at a molecule as a graph, right? So the atoms here are the graph nodes, and the bonds are the graph edges. Now, of course, for molecules, it is a little bit special because there are certain structures here that we definitely won't contain. So, for example, there's a ring here. So, to generalize the edges that contains only bonds, we actually also use so-called hyper edges to contain things like a ring. So these hyper edges are actually a generalization of edges that contain only two nodes. But for simplicity, I'll keep using the terminology of edges when I'm describing this work. So now that we know that a molecule, we'll be looking this by using the graph representation. So the next step is what exactly is the grammar? Here I show an example of the grammar, which contains 4 production rules. So the first rule, which is here, starts from an empty state X, which says that nothing. And then we'll be replacing this empty state by using a ring. Now, inside this ring, there are some nodes that we know what they are. For example, these blue nodes, they are the specific atoms. But we also have the open nodes, which are the R star, the little black square here. These are open nodes, and we don't know what they are, but they can be replaced if there is a match by using some other production rules. And as you can see here, for all of the production rules, the left-hand side is something that contains the open node R star, and then the right-hand side says that we'll be replacing that by adding edges and bonds. So this is exactly the way that we compose a graph, which is to iteratively add nodes and edges until eventually the entire object we have. So let me give an example. Now, here we start from the empty state X, and iteratively we'll be applying certain rules to expand the graph until eventually there is only open nodes. For example, in the first step, as you saw in the past slide, we'll be using the first rule to replace the empty state by the ring. And afterwards, we see that there are two open nodes in a ring. So we'll be applying another rule that replaces these two open nodes by another ring. So now we have two rings, but still inside the rings, there are some open nodes. So we'll be further applying applicable rules and expand the graph and do this multiple times until eventually there's no any open nodes in the graph. That is the graph that we want.
So, Jie, I imagine this is a very simplified example with 4 production rules. How many production rules would you expect in general in like a real example?
No, so that actually entirely depends on the training data set.
Okay.
For example, for this particular example here, we're actually using a training data set of isocyanates, and there are only a dozen molecules. From there, we can actually learn a grammar that contains the production rules to generate all these isocyanates, and the number of rules there, roughly 5 or 10.
Okay.
So it really depends on where you learn from.
And maybe just jumping in on that. So in the first step, you basically come from an empty set, and then you have like some scaffold of molecules. So I expect that there are like more of these rules, right? So it's not just one that can generate something from an empty set, but more of those, right?
Right. So the initial state where the rule that starts from an initial state. So this is actually a very special rule, and depends on the training set and depends on what eventually we learn about. It is possible that there's only one rule that says that starts from specifically the start state. So in that case, it basically says that every time I'm going to start with this ring here. But it is actually also possible that the grammar we learn eventually would contain multiple rules that contains the start states. And then in that case, we actually have to choose which rule to use when we generate the molecule. So there is actually a very natural question, right? So how do we get these rules? How do we get a grammar? Now, the way to get this grammar is actually the reverse thinking. So rather than starting from the empty state and get the final graph, then we'll be actually starting from the complete graph and then try to strip off the graph component by component until eventually nothing remains. So for example, what you see here is that we start with a molecule, and then in the first step, we'll be removing these 4 nodes here and replace it by an open symbol R star. So because of this reverse thinking, the production rule actually says that we'll be replacing the open star, the open node R star by these 4 nodes connected by the edges. Right. So every time we strip off a component from the graph, we make a production rule until eventually we make enough production rules so that nothing remains. So this is the way that we can get a grammar, which if we apply reversely, we get a graphs.
Yeah, it's actually amazing because what you can see here, and I mean, this is also an example that fits to the set that you showed. It actually has rules that generate real chemistry, like chemical functions or chemical entities that have a function in the
Exactly.
end.
So later on, I'm actually going to show you some specific experiment results. And from there, we can see that certain functional groups for a certain class of molecules are actually appearing in these production rules that we learn. Right. So now that we talk about how do we learn production rules, but now we actually also have an open question, because the way that we define what components to strip off and the order of stripping these components are actually arbitrary. So what would be the best production rules, or what would be the best grammar? So we inject the machine learning here in order that we can get an optimal grammar. Now, the way we do this is that we'll be imposing probabilities for the edges, because these probabilities will be telling us with what components are formed and what components are removed. So then we'll be doing an optimization loop. We start with an existing grammar that contains the production rules, and then use the grammar to generate a large set of molecules. And then we measure how good these molecules are. There are multiple indicators. For example, we can measure how many of them can actually be synthesized. or we can measure whether or not they are diverse enough to cover the entire space. So whatever they are, we'll be using these indicators and go back and specify and update better edge weights. So these edges would give us another set of grammar rules, and then we iterate and do this loop until the optimization converges. So when it converges, the grammar we get will be the one that generate molecules that are synthesized, that are synthesizable maximally, and that are also maximally diverse.
That's actually great, and I want to jump in on that because generating molecules is easy, right? I mean, you can just draw it on a piece of paper, but generating molecules that are actually synthesizable, that is the challenging task, because you do not want to spend like hours in the lab until you eventually find out that you can probably not make that molecule, but you want to have like molecules in a set that are predicted somehow that you can actually make in the end. Because it doesn't matter if a molecule or a hypothetical molecule has brilliant properties, but you cannot make it. So it's probably just something that you can just throw away right away, right?
Exactly. And I think this is actually also one of the great things about these methods. Because if we look at existing methods in the literature, many of them, when they learn the generative model, they only consider how well you can reconstruct the original training examples. But now we are actually not considering how well we can generate existing training examples, because the grammar itself actually guarantees that. So in addition, what we do is to look at other indicators. And one very important thing is the synthesizability, right? So we'll be using that as an indicator and try to optimize our model so that eventually we can generate as many molecules as possible, which are synthesizable.
Yeah.
So maybe let's look at some experimental results. I hope that I can actually convince you further that we're actually doing a great job. Right. So what I'm showing here is that we have certain methods to compare with and certain metrics that we also compare with. So the bottom one here, the DEG, is our method, which stands for data efficient grammar. On the top, some state-of-the-art AI methods used for generating molecules. So actually, many of them are also in a style of encoding a molecule into an Euclidean latent space and then coding them back to the original molecule. So when we compare them, then we look at various different metrics. For example, how many of them can be synthesized is definitely one thing that we focus on. But additionally, we also look at other metrics. For example, when we look at existing generative methods, they are actually treating the training set as a distribution. So when they build a model, they want to generate data that forms a distribution that is aligned with the original distribution. So we have all these 4 metrics that measure how well such alignment of the distributions are. And then, unsurprisingly, we also have a metric that just tells us what is the proportion of the molecules that can actually be synthesized. Yet, one more interesting thing is that we have another metric, which is called membership. So this membership is particularly talking about if our training set consists of a class of molecules, right? So there is a specific class here. So when we generate, then do the generated molecules also fall under this class? I think this is actually one of the very rare things that we also compare when we are evaluating our methods. And for all these metrics, obviously the higher the better, right? So you see that for many of the metrics we are actually achieving the best. And even for the one here, which is possibly the second, but it is actually still close to the best. So this is for the isosceles class, and what is not shown here are actually also some other training sets in some other classes, and the results conclude similar findings.
It's good to see that actually in action, because I mean, you briefly touched, like, there are other methods that can generate valid molecules. Like you get a molecule that actually is a molecule and does not have like a carbon atom with 5 bonds attached to it or something like that. And in that region, we see that there are methods that are probably doing equally well like we do, right? 100% valid molecules, brilliant thing, good to go. But the interesting thing that you touched at the end, like the synthesizability and the membership, we can see that this method is actually outstanding there, because getting to I mean, this RS value of 27% basically means
that means retro score. So that is actually one of the tools that we use to measure the synthesizability of a molecule.
Exactly. Good that you add that. I mean, it's on the bottom, right? Synthesizability. And that's actually something that we want to have, as I already mentioned. Like it should be synthesizable, but also many of the challenges that we face are in the last column that you have here. Like they should be of a similar chemistry, because usually if you have like a certain chemistry in your company, you do not want to generate like arbitrary molecules that somebody could eventually make. You want to make molecules that you can make and that fits to your portfolio, right? And that's actually very nice to see that we can actually have membership scores that are amazing, right?
Yeah, it's just like, I mean, sort of, you give me some isocyanates and I will generate isocyanate for you, but not something else.
Exactly.
Jie, I have a question for you. What do you think it is about this method that is leading to these strong results that's different from some of the alternatives that are listed here?
I would say, so one important thing is about the data efficiency, as I mentioned at the very beginning, right? So a lot of methods here, like the graph MVP or GTVAE, all these methods are deep learning methods. They require a large amount of training data. So as a matter of fact, when we are doing these very particular data sets, isocyanates, I mean, so there are only a dozen, probably less than a dozen training examples there. It is just because human beings actually don't know more than that. So then when we are trying to deal with these data sets, it is very natural that existing methods, which can only work with large data sets, would likely fail.
I see. That makes a lot of sense.
Right. Perfect. So then maybe let me also show you some other examples, just modern numbers, right? So what I'm showing here is that for different data sets, we can generate new examples. Like, so all these are newly generated ones, and I don't know. So Thomas, you are actually experts. Do you actually? Is it possible that some of them you actually haven't seen them before? Which really says that we are generating something that you're curious about.
Well, you can always draw them, right? But the interesting thing is mainly that you put in like that little amount of data, only 12 examples of a particular molecular class, and you actually are able to learn what you had, like the language of that particular data set. And so what I love to see here is that you actually generate isocyanates if you throw in isocyanates, and that doesn't have to be the case if you just use some other method, right? And I mean, you can basically draw each and every molecule. So that's what I meant with it's easy to just draw them on a piece of paper. But those seem, I would say, at least reasonable, right? So you have like the functional group that you're expecting, and you have something carbon-based in the middle, right?
Speaking of isocyanates, I mean, so let's look at what exactly these production rules are, because we're actually all curious. I mean, so why do I exactly generate isocyanates? Now, we play with three data sets again here. So, and we show some of the example production rules that we learned from the training sets. And if you look at, for example, the top rule, so this is for isocyanates. And if you look at the first rule and the third rule, we explicitly see the functional group here, which contains the nitrogen, the carbon, and the oxygen connected by double bonds. So these are the exact things that we expect to see for isocyanates. And you know what actually is the production rules? Actually, we learn these production rules, and we learn these production rules by not hearing someone else telling us that, hey, you really need to have N and C and O and connected by double bonds, but we really just look at the training data sets and the algorithm can figure it out.
Yeah, and if I look into that rules that you generated just for the isocyanates as an example, it's also nice that you don't get any other functionalities, right? Because if I want to have like an ester or an acrylate or something like that, I would put it in my data set and then I can generate those. But I only put in isocyanates, so I'm basically generating only isocyanates. And that's actually pretty amazing.
I'm glad that you like it. All right, so yeah, I think that is actually pretty much the work that we've been doing recently. I mean, so one thing that excites me about this is that the methods that we're using, or the method that actually we developed, is making a very innovative use of graphs and grammar. And this allows us to train a model that uses only a very limited amount of data. So it is super data efficient. Right. So, and we hope that this method will actually significantly speed up the process of identifying more useful drugs and materials. And because in real life, we just don't have that many molecules to start with.
Absolutely. And so, Thomas, I want to ask you that question.
Yeah.
In real life, do these methods support the work that you're doing?
Yeah, hopefully. So traditionally, if you generate molecules, you always rely somehow on the creativity of a chemist. And we definitely want to embrace that creativity that a chemist has, but we want to support it with some kind of, I would say, artificial creativity. So that's what we do. Yeah, we learn a language. We learn the language of a particular data set, and we can give our chemists like just pictures of new molecules that they probably never thought about. And if we add then the property prediction part of it that you also mentioned in the beginning, that becomes a very powerful tool to quickly identify, okay, which routes can I actually navigate in my chemical space, which would give me superior properties of what I actually already know.
Mm-hmm. So it sounds like both are really valuable pieces of the process, the generation, but also the property prediction.
Yeah, definitely. And also, it becomes in handy that this method is actually pretty data efficient. So we can also, in principle, describe the molecules in a very efficient way, which gives us probably a little bit more breathing space to do the property prediction on very limited training data. Because, I mean, if you have data for 12 molecules, that's not much. But if you look into the chemical industry, it often happens that you do not have billions of molecules, but more like in the probably tens to hundreds, where you can actually effectively generate data.
Right. And is that a question of being able to generate data, or actually even just having knowledge of the molecules existing?
Well, what we always have to keep in mind is that generating data in chemistry usually is not like pushing a button and then you get a result for a molecule. You have to think about, how do I make that molecule? Then somebody has to go out with it and probably perform a multi-step reaction to get a molecule, and then perform some other reaction on it to get, for example, polymeric data, right? And that can be actually quite broad. So it is actually also something which has to take the cost in mind, because it's very costly for us to generate knowledge on molecules.
I think this real world perspective is so helpful, because I know that a lot of the work we do here at the lab, we use publicly available data sets or images or words and things that, unlike molecules, maybe are a little bit easier to come by. So while we have not infinite data, we certainly have often more than 12 examples.
Yeah.
So I think having that perspective of knowing this type of use case, there's a real natural bound to the amount of data we'll ever have, really highlights the importance of having methods that are able to address that.
Yeah, that's definitely true. I mean, it's easy to take a picture, right? And if you train something on cat pictures, you can just take more cat pictures, right? But it's probably little bit harder to generate data on molecules. That's definitely true.
Yeah, absolutely.
I would say, I mean, so as I mentioned at the beginning, right? So our next step would be looking at how can we predict the properties by using computer methods, and just getting back to this data efficient paradigm, right? So data efficiency is actually not only a benefit of our methods when we generate molecules, it is actually also something important when we are trying to develop a prediction model for the properties. That is something in our agenda next, and we actually will be so excited to see how we can use this grammar, and particularly the production rules and the ordering of using the production rules as a good representation for the molecules when we are building these predictors.
Yeah, I'd love to see that.
Well, on that note, I want to thank both of you for taking the time to talk with us today. And I also want to thank our audience for listening in. It's been great. And we will be back again soon. So stay tuned and we'll see you all soon.